The IB keeps repeating these standing wave questions. I analyzed 5 years of past papers and the pattern was obvious. Same wording, new disguise. So based on that, here's my prediction for the 2026 paper. Let's solve them before they ask it. Let's solve the first question. A stretched string of length L is fixed at both ends. A standing wave forms with 4 nodes, including the ends. Which expression best represents the displacement pattern of the string? The question says we have a string connected at 2 ends, those 2 ends being the nodes, meaning the string cannot move. And in between we have 2 more nodes. So let's maybe plot this standing wave. The standing wave would look like this. A node here, another node here, another node here, and another node at the very end. We know that the total length is L, meaning that this entire distance is L. That means the distance from the first to the second node is L over 3. So at L over 3, the displacement has to be 0. That means if I plug in x equal to L over 3, the correct equation should go to 0. If I do it over here, if I plug in x as L over 3, L and L goes, we get sine pi over 3. That's not 0, so option A is incorrect. If I plug in x as L over 3 over here, L and L goes, we get sine 2 pi over 3. That's not 0, so option B is incorrect. But if I plug in sine x as L over 3, L and L goes, 3 and 3 goes, we get sine pi. And sine pi is 0, meaning C could be a correct option. What about D? If I plug in x as L over 3, L and L goes, we get sine 4 pi over 3, which is not 0. So the correct option is option C. Let's move on to the next problem. A rope is vibrated so that the distance between the second and sixth antinode is 90 centimeter. What is the wavelength of the wave on the rope? Before we solve this question, let's sketch the wave. The sketch would look like this. This being its first node, the first antinode, the second antinode, third antinode, fourth antinode, fifth and sixth antinode. We are given that the distance between the sixth and the second antinode is 90 centimeter. So this distance is 90 centimeter. But these are 2 wavelengths, one wavelength and another wavelength. So 2 wavelengths make up 90 centimeters. This means 2 lambda is 90 centimeter. This therefore means that the wavelength has to be 45 centimeter. And that solves this problem. Let's move on to the third one. A vertical tube, open at the top and close at the bottom, has a fundamental frequency in air of 220 Hz. The speed of sound is 340 meters per second. Show that the length of the air column is about 0.39 meters. Let's make a sketch of this problem. The sketch shows a tube that is closed at the bottom and that is open at the top. The green line shows the fundamental frequency of air. Note that this is an antinode, as it should be, and this closed end is a node. The fundamental frequency is given to us, the speed is given to us, so we can use the wave equation which says V equals lambda F. This means that lambda will be V over F, which is 340 divided by 220, which is 1.54 meters. So we got lambda, but how do we find the length of this column? Let's extend the wave beyond the tube. The wave would go on, curve down, and turn and go in the negative direction. This distance over here, from here to here, is half a wavelength. This means this distance is quarter of a wavelength. So quarter of a wavelength is the length we are looking for. L, the length of the tube, is quarter of a wavelength. Wavelength we already found, so we just substitute 1.54 in this equation. If we do that, we end up with a length of about 0.39 meters. And that completely solves the problem. I will attach this PDF in the description below for you to play with these questions on your own. Share this video with your friends. I'll see you next time. Happy learning.